want to thank you, Engineer Uche. We want to keep to our time. So today, last week, we went through introduction to solar system, talking about the technology, different types of solar PV models, how the solar PV is rated, how the conditions of standard test conditions, the energy yield, and some of the things that affects the output of PV models. So we discussed all of those last week, and successfully we ended that module last week. Today we're going to be looking at solar PV design and sizing. So today we are going to try as much as possible to talk into practicality of solar PV system, especially when it comes to design and sizing. How do you size your solar PV model? Where do you start from? And how do you run the calculations for your PV model, your battery storage system for batteries, those that has battery storage? How do you size your inverter? How do you size your charge controller? So we're going to go through all of that in today's presentation. Okay, this is about me. For those who are just joining in, who didn't participate last week, my name is Chimamoneke. I'm a lead consultant at Schematic Blue Energy, a certified energy auditor, as well as a certified energy manager. I have background in engineering with more than 10 years professional experience in energy sector. So we're just going through, going straight ahead to the discussion of today. We're going to be talking about solar PV design and sizing. So sizing a photovoltaic system, PV for short. Now, this is for standalone PV system, and it involves 5-step processes, which will allow the photovoltaic system designer or user to accurately size a system based on users' projected needs, goals, and budget. Now, these steps are as follows. The first thing is estimating the electric load. PV systems are meant to power electric load. So first thing you need to do is to determine the required size of electric load that you want to power. The next is sizing and specifying an inverter, followed by sizing and specifying the batteries, then followed by sizing and specifying an array, like the PV models or the PV array. If you have strings and different strings of PV models, then it becomes an array. Then you also have to specify a controller or charge controller, as many of us know it today. So let us start from estimating the electric load. If you want to install a PV system, the first thing that you need to do is to sit down with a client and then ask some pertinent questions. What do you want? Why do you want to install this PV system? What are the loads you want to power? So, but at the end of that discussion, you should come up with a table like this, what you're seeing on the screen. Where you have the name of the equipment. Now, it doesn't have to be accurate, but you need a rough estimation. The client should be able to tell you as much as possible the equipment that he or she wants to power. And it is very important that you also may want to ask the client, beyond this equipment or beyond these tools, electronic equipment that he has listed, are there other equipment that he may want to power, such that you can be able to advise. You may not necessarily need to consider those equipment in your design, but you can be able to advise, right? So it is possible that the client could still use some of those equipment, but for him to use those equipment, he needs to, implement something like an energy management. So for example, he wants to use some equipment, he might need to turn off the fridge, turn off the some of the loads in this list, and then be able to power those, if at all your design can be able to power those equipment. So those educations are also important for your clients. So, but let us just run through these details we have on our screen. So we have 4 items here. We have the television. The client has 2 television that he wants to power. There's a fridge, one refrigerator, light bulbs, 8 light bulbs, and they have standing fan, one standing fan. So these are the basic things that these clients wants to power. And these are their ratings. The television is 50 watts, the fridge is 150 watts, the light bulbs is 15 watts each. And then you have the standing fan at 40 watts. So all the power demand for this client is 410 watts. Okay, so this is more like a basic energy audit, right? Where you need to, do a load inventory for the things that need to be powered by the solar system. Then you also need information on the usage of those equipment, and this will enable you to be able to size appropriately the battery that should be able to sustain those load for the time that the client wants to use them. So for the TV, the client estimates that he will be running the TV for 6 hours, the fridge will be running for 12 hours, the light bulb will be running for 8 hours, and then the standing fan will be running for just 1 hour. So if you multiply the rating, that's the wattage, the total power demand for each one of these equipment with the usage hour, you will come up with the energy that it's going to draw for 1 day. So the energy that is required to power that equipment for 1 day, this will be critical when you're doing your battery calculation, or when you're sizing your battery. This will be very, very critical, because battery stores energy, not necessarily power. And this power will be critical when you're sizing your inverter. Okay, so this is synonymous to your generator. So this is a sample table that you need to come up with. After discussing with your client, you need to come up with this table. 2 things are very, very important: the power that the clients require, the power demand, and the energy that is energy requirement. Wow. These are 2 critical information that are required. Now let us size the inverter with this collected information. So from what we can see here now, the peak power demand for this client is 410 watts. 410 watts, not kilowatts, 10 watts. If it's kilowatts, you divide by 1,000, it becomes 0.4 kilowatts. But this is 410 watts. So now we want to size an inverter for this client. It is possible that you can look at this and say, okay, the client needs 410 watts. Let me go to the market and perhaps let me look for 400 watts inverter. Now, some inverters are rated in watts, some are rated in kVA, right? So we need to also be careful when we're looking at the units. Kilowatt or watt is not the same thing with kVA, and the difference is power factor. We are going to see how to use that, when calculating for the size of the inverter. So when you have this peak demand, 410 watts, it does not mean you should go for an inverter of 410 watts and give the client. Now, if you do this, what you've done is that the inverter will be working at 100% load anytime all of these equipments are switched on, assuming that they draw this amount of power. Then the inverter will be at 100% load, which is not ideal, right? So we usually have something like we call tolerance, okay? So, and what actually defines that tolerance is load factor. So at what load factor do you want the inverter to be, okay? When it is 400, when the inverter is delivering 400 watts power, what is the load factor you want the inverter to be, okay? So it could be 60%, it could be 70%, it could be 50%, okay? But the highest load factor I will suggest or I will recommend in your design is 70%. The highest load factor I want to recommend is 70%. You could do 50%. It's fine. You could do even 40%, but don't do 30%. In fact, 50% is ideal. Okay, but I wouldn't suggest you go beyond 70%. So what this means that you have to divide, so sizing your inverter now, you have to divide your peak demand by your load factor. Okay, so that will give you the kind of tolerance that you need. So if you divide 410 by 0.7, 0.7 means 70%. You will have 585.7 watts. Okay, 585.7 watts. Now this is watts, not kVA. And please pay attention. Some inverters are rated in kVA. Some are rated in kilowatt or watts. So pay attention to the unit of your inverter. So this is the amount. So if you're working with watts, as you go to the market and you see, okay, you see the kind of inverter that you want to buy, but it is rated in watts. Okay. So it is fine. You may want to take this. Okay. You may want to take this, but if it's rated in kVA, how do you convert this wattage? How do you convert this to kVA? like I told you the other time, the factor that converts watts to kV or kilowatts to kVA or VA is power factor. Power factor. So if we assume a power factor of 80%, then the inverter size would be 585.7 watts divided by 0.8. You would then have 732.125 VA. This is VA, not KVA. It is very, very important we pay attention. In our previous session before this, not last Saturday, in our previous training before this, we talked about energy and energy basics and energy fundamentals and electric basic, where we talked about some of these units and some of these calculations that I'm using here in this presentation. So we need to pay attention to units. Units is very, very important. So this is VA. If you want to convert this to kVA, you divide by 1,000. So this becomes 0.732 kVA. Okay, if it's VA, it is 732.125 VA or watts. I'm sorry, if you're converting it to real or active energy, it becomes watts. So I hope this is clear. Any questions so far?
No.
No question. Fine and good. So we are going to do a little exercise. It's just a little exercise. So this is an exercise 1. Calculate the inverter size required if the peak power demand is 750 watts. Now, use a power factor of 85%, and the desired load factor is 60%. Now, I want you to calculate the inverter size using these details that I've provided. Now, we are using 60% to allow for future load addition. You know, some people, when they install solar system, there's possibility that they might increase the lighting bulb. They might put external lighting. They might put out light bulbs, you know, on their corridors or in the external security lights, or they might even want to add additional fan. So some of those things you might not be able to envision them at the time you're doing your design. But it is expected that maybe over time that client might want to add 1 or 2 things. So create that tolerance. That's why we're using 60% or 70%. So please, can you work on this exercise? And then let's know what you got as your answer, please.
382.5 watts.
Put it on the chart. Just put it on the chart. Put it on the chart. Thank you.
Yeah. 742.
I think I can see 2 people has posted. Is anybody struggling with this? Because I think by now we should be done with this calculation. And now we have, maybe just read some of the answers I have on the chat. We have 1,470.57 VA. And then I also have 1,250 watts. So is anybody getting something different? Okay, I think from all the answers I've seen so far on the chat, everyone is correct. Even though some, okay, Odunayo, Lanre, you have 1,470 watts. Is that watt? It should be it's not watt, it's VA. So unit is very, very important. So Lanre, your answer is correct, but the unit is wrong. If it is watt, it is 1,250 watts. So if you're getting 1,470, then it is VA. Okay, so let us pay attention to the unit. Okay, so let's just proceed. From the answers I've seen so far, I think everyone got it correct. So that's about the inverter. Now we are done with the sizing of the inverter. Let's just look at the battery system. Okay, how do you size your battery system? So now remember we are working with a daily energy need of 3,400 watt hour or 3.4 kilowatt hour. That's the energy storage need for one day for this client. Okay, now there's what we call days of autonomy. Now there's no guarantee that the sun is going to shine every day. Okay, so the thing is, what if the sun does not shine for 1 or 2 days? What happens? Does it mean that the client will not have power? Does it mean that the client will have to switch on generator? So what do we do? Okay, so we call it days of autonomy. So you could also ask the client, how many days of autonomy do you want me to design this storage unit for, right? So even if there's no sun for 1 day or 2 days, you have enough battery storage that can last you for those periods when there is no sunshine. And that is what we call days of autonomy or backup system for non-sunny days. So in our design, we need to consider that as well. So our daily energy need is 3,400 watt hour. Now we have what we call the days of autonomy. We want to add 2 days of autonomy to our energy storage. So if the sun does not come out for 2 days, we want to be sure that our client is still connected. Our client still has energy that is stored that can last him or her for that 2 days. That's what days of autonomy is. So now we have 2 days of autonomy plus our normal active day, okay, the last day before the sun refuses to shine for the next 2 days. So that's 3 days. So we are designing for energy storage that can last the client for 3 days. In some cases, it could just be 1 day. Days of autonomy could just be 1 day. In fact, in some cases, that you don't need any days of autonomy. If there's no light, I will run my generator. So you need to have that conversation with your client and then design as appropriate. But in this example, we're using 2 days of autonomy, 2 days plus the normal day that the sun, the last day of the sun. So we're having like 3 days. So we are designing a storage system for 3 days. Okay, so if you multiply 2,400 watts hour by 3 days, you have 10,200 watt hour. Okay, so but this 10,200 watt hour is this usable. This is the usable size of our energy storage. Okay, now there's what we call depth of discharge in battery system. Now for batteries, especially for lead acid, typically for lead acid batteries, they usually have a depth of discharge of about 50%. What that means that you can only take 50% of the energy stored in that battery and then leave the 50%. Okay, and then you charge that battery up again to 100%, use 50%. Okay, so that is what we call depth of discharge. You don't discharge the battery entirely. If you discharge the battery entirely, you will damage that battery. The battery most likely will be damaged and it will not last long. So this is a safety measures in using batteries. Okay. So now this 10,200 watt hour is what you can take from the battery. So it's just about 50% of what you can take from the battery. Okay. So now to determine the actual battery size that you need to divide this your 10,200 by the depth of discharge, which is 50%. So if you do that division, you will have 20,400 watt hours. So the entire battery size that you need is 20,400. So that at 50% depth of discharge, you will have 10,200 watt hour. So that is the logic. I hope this is clear.
Yes.
Okay. Okay. Now let me explain something again in calculating the energy content of a battery. When you go to the market to buy battery, in some places they will rate the battery in kilowatt hour. So they will say that, okay, this battery can have an energy storage of maybe 2.4 kilowatt hour, especially for lithium iron phosphate batteries. Most of them are rated in kilowatt hour. That is energy that they can store. But in some other battery, you will not see the kilowatt hour. You see voltage, you see current. So you see something like 12-volt battery, you see something like 200 amp hour, you see something like maybe 24 volt. So depending on the kind of battery you're seeing. So what I want to establish here is how you can be able to calculate the energy that the battery can store when it is not given. So if you're told that your battery is 12 volt and 200 amp hour, how do you calculate the energy in terms of kilowatt hour? That is what I want to establish here before we proceed. So most batteries are rated in voltage and amp hour, okay? Now we know that power is equal to voltage times current. Power is equal to voltage times current, then times power factor for you to have an actual real power. Now, energy is equal to voltage times current times time. That is energy, right? Okay, now we know that this amp hour that we are seeing here is current times time. This current times time is amp hour. So we see amp hour in our battery. What that means is already current times time. Okay, so this current times time times the voltage. So when you multiply current times time times the voltage, you have the energy that battery can store, right? And which is now watt hour. If you divide it by 1,000, you have kilowatt hour. I hope this is clear. So let us now proceed with sizing of our battery. So calculate the number of batteries required to produce 3.4 kilowatt hour or 3,400 watt hour of daily energy need plus 2 days of autonomy for cloudy or non-sunny days using lead acid batteries with the following ratings. Now, this lead acid battery is a 12-volt battery, it's 200 amp hour, and we want to consider a depth of discharge of 50%. A depth of discharge of 50%. So what we want to do, we want to calculate the number of batteries that we can install for this client so that for 3 days, including 2 days when there is no sunshine, this client can still use this system. So overall, we want to extract about 10,000 or 10 point something kilowatt hour for this client, right? So here is what we'll do. Now, his daily energy need is 3.4 kilowatt hour or 3,400 watt hour, right? That is daily energy need. Now, we want to consider 2 days of autonomy. So 3.4 kilowatt hour times 3 will give us 10.2 kilowatt hour. Now, the actual battery size at 50% depth of discharge, it's that 10.2 kilowatt hour divided by 50%, that is 0.5. So when we run that division, we'll have 20.4 kilowatt hour or 20,400 watt hour. So this is the batteries, this is a battery bank. This is the size of the battery bank that we need to install using lead acid battery. If we are using lithium iron phosphate, which might have a depth of discharge of about 80%, it will be less than this. Now, this is dependent on the battery technology you're using. But we are considering, our question says we are using lead acid batteries. And our depth of discharge is 50%. So that's what we are trying to do here. So specific energy storage of one of the batteries. So one of the battery, remember we told us that it is a 12-volt battery and 200 amp hour battery. So what is the energy? What amount of energy can one of the battery store in terms of kilowatt hour? Okay. So one of the battery can store 12 volts times 200 amp hour is equal to 2,400 watt hour or 2.4 kilowatt hour. So one of the battery can actually store 2.4 kilowatt hour. So what we're going to do, we're going to divide this 20.4 kilowatt hour by 2.4 kilowatt hour to get the number of batteries that we need to install for this client. And that's what we did here. Total number of battery requires is 2.4 kilowatt hour divided by, 20.4 kilowatt hour divided by 2.4 kilowatt hour, which is going to give us 8.5 number of batteries. 8.5 number of batteries. Okay. Now, you have 8.5. You cannot have 8.5 battery, of course. You cannot. So you need to either ram it down to 8 number of batteries or 10 number of batteries. Now, you may not use 9 number of batteries. Now, the reason is this. Unless your inverter is 12-volt system, unless your inverter is a 12-volt inverter system, you cannot use nine number of batteries. If your inverter is 24-volt system, then you can only use 8 number of batteries or 10 number of batteries. Okay. So let me see. Oluwadami Lare, you were saying I should please explain again. What again do you want me to explain, please? I'm just reading your message now. Unmute your mic and then be specific, please. So I know where I need to explain more.
again. I've gotten what I needed. When you were explaining about the battery, that's where I was saying you should explain again to understand the rows of calculations you did.
Okay, thank you. Did someone raise hand? I don't think so. Did anyone raise hand?
Yes, sir. I raised my hand.
Okay. Go on.
You are saying that if it is 24 volts of 24 volts battery, we cannot use 9 batteries.
Yes.
Why is that it must if it is 24 volts, then all the batteries must be in even numbers, or I don't know. Let's just assume that what we get is 17. So if it is 24 volts, that means we cannot use 17 too. So
yes,
that's what I want to know.
Okay, thank you very much. Yeah, now that you've asked the question, let me just throw a light on it. I will still talk about it later, but let me just throw a light on it. I said if you have an inverter that is 24-volt inverter, what that inverter needs, the input that inverter needs is 24 volts. Now your battery is 12 volts. So you need 24 volts to go into that inverter. What that means that you're going to connect 2 batteries in series to have 24. So you must connect 2 batteries in series to have that 24 volts that you can feed into that inverter.
Right.
You cannot feed 12 volts into that 24 volts inverter. It will not work. So you need to combine 2 batteries. So if you're combining 2 batteries, what means that you cannot use 9? You must combine 2 batteries to get 24. If you're using 9 batteries, you combine 2 batteries. If you combine 2, that is 4, which will give you 8. Then you have only 1 battery that is remaining with 12 volts. So you cannot work with that. So that is the idea. Unless your inverter is 12-volt inverter, then yes, you can use 9 number of batteries, because you can feed in the individual voltage from the batteries direct to the inverter. In which case you are just connecting in parallel. So we are still going to come to series and parallel connection, where I will explain more on this. Okay, so just if it's still not clear to you, just hold. We are going to talk about series and parallel connection, where I will talk more about this.
Okay, sir, I have a question.
Okay.
Please re-explain about that days of autonomy. You said usually we used to take 2 days.
Your voice is faint. Can you speak up a little bit, please?
Those days of autonomy.
Okay.
Please re-explain about it, because I did not understand. In the question, we do have 2 days, but during the calculation, you take 3 days. I did not understand. How did you do that? That's
okay.
My question.
Do you understand what I mean by days of autonomy?
Yes.
Okay, fine. So now you need to size your battery bank for 1 day, which is 3.4 kilowatt hour. That is 1 day. Okay.
Yeah.
Now you need additional 2 days of autonomy that the sun might not be able to come out.
Okay.
You need additional 2 days. So those additional 2 days plus your initial 1 day of your battery sizing. So you're sizing your battery. Yes, you're sizing your battery for 3 days.
Yes.
Okay. If you want to use 2 days, you can say, okay, my days of autonomy can be 1. Okay. Then plus the actual number, the actual day that the sun is going to shine. Then after that day, the sun is no longer going to shine. Then that's another 1 day.
Okay, I understand. I understand what you mean.
Yeah, so that is the understanding here. That is the analogy, all right, for you to be able to times this your daily energy requirement by 3 to have 10.2 kilowatt hour.
Okay, I understand.
Okay, so let's proceed. So now we know the number of batteries that we need for this client. It's either we use 8 or we use 10. Okay, so here's another exercise. This is exercise number 2. Now the question says calculate the number of batteries required.
Sorry, can I ask one question, please? Sorry.
Okay.
Because if you check the previous slide, that when you were talking about having an actual wattage or the kilowattage, that we can multiply by the power factor. Can we multiply by the power factor at this stage as well?
This is the previous slide you're talking about?
Yes. So if we want to get the actual power watt, we can always multiply all of it with power factor. So is it necessary in the, because when you do this slide, and the one we work with the example right now, you did not multiply by the power factor to get the actual wattage. Is it necessary, actually? The question I'm trying to ask.
Okay, no. So when you're calculating for your battery, as long as it is in kilowatts, you don't need power factor. You only need power factor when it is in kVA, when it is, now we call it apparent power. But when it is in real power or active power, you don't need power factor.
Right. But if you check the previous slide, sorry, please, if you check the previous slide.
Okay, yeah, here, right?
Yeah, this one. So batteries are rated in voltage and ampere. So if you want to calculate the power, energy, and the energy, you multiply all of the when you want to get the wattage. So how do you reconcile that this one now with the example you've calculated right now?
Okay, so what we have here, if you notice, I put this power, I made it faint.
Mr.
Right?
Chima, Mr. Chima.
Okay. Yes, okay. Someone.
I'm Mahmoud Abdullahi. Let me shed more light on this power factor. I think it's confusing, especially for those that are not electrical engineers.
Okay, please go on.
Yeah, power factor, like Mr. Chima just said, we have what we call real power, apparent power, and all that. But this is as a result of those elements in the load that either store energy or dissipate it, like the capacitors and inductors. So when we did the example for inverters, we use power factor because you are supplying to an AC load, and you have to take care of those powers that will eventually be useless, more or less, because they are not useful power. But because the battery is supplying to an inverter and is supplying a DC, it says DC supply to it, you don't actually need power factor at this stage. We've already taken care of the power factor between the inverter and the load, because the load is where you have your capacitors, perhaps your inductors, that is the reason why you have those
sorry, if I'm allowed to cut, if I'm allowed to chip in, I'm allowed to chip in during the load details, we've already applied the power factor.
Yes, you have applied already. That is why you will not apply, because the load is not taken directly from battery. The load is taken from the inverter. The inverter is the one taken from battery, and the inverter is not a load that has those. You are feeding DC current to it, so you don't need power factor at this stage. So if you understand very well, why you are doing the power factor is just to convert to kVA.
No need,
because you
apply the power factor sizing of inverter. Power factor has been included. We started.
It already has been included at the inverter stage, so you don't include it at the battery stage. I'm just trying to shed light more on the question why we are not going to use power factor at this stage of battery sizing.
Thank you very much, Abdullahi. And the other colleague that also contributed. I don't know if it's clear to the participant that asked this question. And I think this is the reason why Engineer Uche led the emphasis that for those of us who has not gone through there's a video that Engineer Uche shared where we talked about energy and electrical basics. We took so much time to explain power factor in that video. We took so much time to explain so many energy and electrical basics fundamentals in that video, right? It might be of help for some of us who are not electrical engineer, or some of you who are not electrical engineer, to maybe take a look at that video. It's about 2 hours video, so take your time and then watch that video. It will really help to clarify some of these issues. But at this point, there's no need to include power factor here because the power factor has been calculated when we are doing the inverter. So you don't need to include it here again. And like Engineer Abdullahi said, it's DC to DC. So there is no need for power factor at this level.
Yes, so it's clear now, because I asked that question because if you check the captions here, so calculating the energy content of the battery. So if you want to calculate the power, the energies, all of that, So there is a faint power factor in this case.
Mm-hmm.
So that is why I asked the question. I understand now that it's a DC and is like feeding to the inverter. So already inverter has compensated for that power factor. Power factor in mechanical engineering is just like a factor of safety anyway. So
Yes.
so I was actually being concerned since there's a power factor in this calculation for battery, under battery. That was just the reason why I asked. But it's clear now anyway. It's clear.
Okay. Thank you very much.
Please, I have a question. I raised my hand.
Okay.
Can
Sorry,
I
go on.
contribute to this? Generally,
Please.
load can be given in kilowatts and kVA. So what this means is that when you are summing up your load, when it is in kilowatts or watts, okay, you can convert it to kVA by dividing that real power, which is kilowatts, by the power factor. Let's say generally 0.8. So you divide by 0.8, then it gives you your kVA. So what I'm saying is, if load A is watts and then load B is kVA, and you want to take both of them to the same rating, you need to now begin to use your power factor, maybe to take it to kilowatt or to take everything to kVA. When you want to take watt to kVA, to VA, you divide it by 0.8. And when you want to convert it back to watt, then you multiply by 0.8. That's for the load. But like it was said before, when you are dealing with DC, then you don't need to consider the power factor. Most times, the wattage is also the kVA rating. Thank you.
Thank you very much. So in this case, it is assumed that the power factor here is 1. That's the assumption here. Now, the reason why I put this in fence printing is this. If we want to consider the unit of this power here, if we want to consider it to be watts, which is the active power, then there has to be an element of power factor, which in this case, it's assumed to be 1 because it's a DC current. So we can assume it to be 1, right? And that's why I put this in fence color. If we are only dealing with voltage times current, only voltage times current will give you the apparent power, which is the kVA, right? But in this case, since we are dealing with DC power, it is assumed that the power factor here is 1. That's an assumption, okay? And that's why I left it in fence color, just so I can justify using this watts and watt hour here. I hope that's clear. I mean, it's clear now, even though you already affirmed that it's clear. You just wanted that a little bit of explanation. So
yeah, it's okay. It's okay.
Yeah, thank you. So let's move ahead.
Please, I quickly have a question, please.
Okay.
Good morning, all. Sorry, just taking it back to days of autonomy. What do you advise we want as a potential client if installation has to be done in areas that experience a lot of rain, like in say in the south region of Nigeria, where at some times of the year they have a lot of rainfall? How do we, in terms of giving advice to what to be designed? Because of course you won't have a lot of sunlight during rainy season.
So this is subjective and it depends on the availability of budgets. Okay. You know that the moment you begin to increase your battery storage bank, it comes with cost, additional cost. So, but what I would look at is, depending on the capital outlay, the budget of your clients, right? Then there might be other forms of energy that could come, and just for the period. For me, I would probably want to recommend 1 day of autonomy for such a client. But if the sun still doesn't come out, now let's also bear in mind that even if it is raining, that does not mean that your solar panel is not charging or is not charging the battery. As long as the sun is out, it is picking it is charging, only that the intensity of the sun is very low. So the rate at which it's going to charge that battery is going to be drastically reduced. Okay, so let us not have in mind that there is no day that the panel is not going to work. The panel is going to work, and it might charge the battery, but slowly, very slowly, right? So let us not just have it that the batteries are not going to, it's going to be charged. But for me, I would maybe want to advise that, okay, maybe 1 day of autonomy, but if the client insists that he wants to have an extra days of autonomy and the budget can accommodate that, why not? Okay, so it's really subjective depending on the other sources of energy that is available within the client's reach, and again, the budget of the client. So if it's a place where the grid is available, why will I want to recommend that the client should keep extending the days of autonomy? It's possible that those batteries could be charged through the grid. So there is no one size fits all. They are specific to every project. But what I want you to understand here is understand what these things mean, and then you can now begin to find, when you're discussing with your client, you can now, okay, weigh the options on the table. Like I just mentioned now, it's possible that the grid is also there, which means you can also charge those batteries through the grid, right? And that's where you now begin to recommend the kind of inverter that you need to install. Should you use a hybrid inverter that could also charge from the solar panel and charge from the grid? Or should you use just a battery inverter that is not hybrid, that will just maybe charge only from the solar panel, right? So I mean, there are strategies to this. So I don't know if you're satisfied with that explanation.
Yes, it is. Thank you very much, sir.
Okay. Okay, so let's just proceed. There's an exercise here for us to attempt. So let's just quickly work on this exercise and let's see what we can arrive at. So this is asking us to calculate the number of battery required, assuming 1 day of autonomy is required using lithium-ion battery with a DOD of 80%, and the voltage of the battery is 12, and then the current rating is 100 amp hour. So let us just do a simple calculation on this and then estimate the number of battery that is required for this same client, but using just 1 day of autonomy. So I'm seeing two different answers. Someone is saying 4 batteries, another person, Akorede said 4 batteries, and then Muhammad said 7 batteries. So let me see what others have. Oluwadambi Larry said 4 batteries. Okay, so we're having between 4 batteries and 7 batteries. So the answer you get, whether you get 4 batteries or 7 batteries, it now depends on the number of days you've considered. Remember, we said 1 day of autonomy. 1 day of autonomy plus the last day before the day of autonomy. So you're dealing with 2 days here, right? So for those of you that got 4 batteries, I want to assume that you only use 3.4 kilowatt hour or 3,400 watt hour, whereas those of you that got 7 batteries, you use 6.8 kilowatt hour. Okay, so the right answer for me here is the working with the 6.8 kilowatt hour, because you have 1 day of autonomy plus the last day, the day before the 1 day of autonomy, that is 2 days, right? So if you do that, you should be able to come up with about 7 batteries. And that's the right answer here. So you're dealing with 7 batteries. And again, remember that if you're dealing with a 24-volt system, then it has to be 8 batteries. You have to increase to 8 batteries. So so that is the calculation for this sizing of the battery. Let's move ahead to the next. Okay, so sizing of the solar PV array, right? You need PV arrays that can be able to generate this amount of energy that you can store in your battery, right? So using the sample load details and data from the previous examples, so we need to calculate the amount of solar that we need to install for this client. Remember, we are dealing with a client here. We have established his, we assume that he needs 2 days of autonomy, and we assume that he's using lead acid battery at 50% DOD. Okay, and we have established the size of the battery that is required and the number of battery we need. So let us look at the PV, the size of the PV that we need to install for this client. So using the same load and every other details that we have before now, the required solar PV energy output. Now remember that your PV is what your PV is producing is energy, right? So the capacity of your PV panels times the hours of peak sunshine. Remember when we did that calculation, we give you the energy output. Okay, so we want a PV that can give us an energy output of 20,400 watt hour or 20.4 kilowatt hour, whichever one. So we are looking for a PV that can give us this output. And for us to calculate that, all we need to do is to divide this required output from the PV, divided by the peak sun hours. Okay, so let us assume that the peak sun hour is 5. Peak sun hour is location dependent, but let us assume that the peak sun hour is 5. And remember when I talked about peak sun hour in our last class, I told you that if your installation is around the south region of the Nigeria, you may want to use 4 because there is less amount of sunshine in those regions. But if you're dealing if your installation is somewhere around the northern part of Nigeria, you can use 5 hours. Okay, so it is region or location dependent. But in this case, let us assume that this client is in Abuja and we want to use 5 hours of peak sun hour. Let us use 5 hours. So we are going to divide this total energy that we want this PV to produce. We are going to divide it by 5. So when we do that division, we are going to have 4,080 watts. When you divide 20,400 watt hour, when you divide it by 5 hours, so this hour we cancel this hour, you're remaining with watts. So you have 4,080 watts. But this is theoretical at standard test condition. This is what the PV will give you. It does not mean that when you store this amount of PV, the PV will give you this. There are some losses. There are wiring losses. There are other losses along the line in your installations. So you need to, and all of those losses are what we consider to be performance ratio. Your PV is more like a tolerance too. Your PV is not going to perform at the standard test condition unless you give it the same condition at standard test conditions, right? So let us now calculate the actual size of the PV. So the actual size of the PV will now be this theoretical size of the PV at standard test condition divided by the performance ratio. Remember, we've talked about peak sun hours and performance ratio in our last class. So we're going to divide the theoretical output from the PV by the performance ratio. So we assume the performance ratio in this case to be 75%. So assuming performance ratio of 75%, the actual PV size will be 4,080 watt divided by 0.75. So the PV installation will be 5,440 watts. That's the PV size that we can install that will give us this amount of energy output for peak sun hours of 5 hours in one day. So we need to install this amount of PV. Remember that PV panels are rated in watts. So if for example we have 300 watts PV panel, so let's just check this within ourselves. If we have 300 watt rated PV panels, how many panels do we need to get 5,440? How many panels do we need? Assuming it's a 300 watt rated PV module. 18. Okay, so I see the answers in the chat. We need 18 of these panels. okay, to get this amount of output. Okay, so that is it for calculating the PV modules that we need. There's another exercise for us. So let us
how do we get the 18? Sorry to intrusion.
Okay. Sorry. Please, I mean, whenever you're lost, whenever you didn't understand anything, please speak up. So the 18 now, this is the total amount of PV power that we need to install. So if we install this amount of PV power and it becomes active for 5 hours, I mean, the sun shines on this PV panel for 5 hours, it will produce this amount of energy. Okay, assuming it's performing at 25% less of its actual capacity. Okay, it will produce this amount of energy. Now, how many number of PV do we need to install to give us 5,440 watts? And assuming that one of the PV panel is 300 watts. One of the PV panel is 300 watts. So we are going to divide 5,440 by 300. So we got 18 by dividing 5,540 by 300. That's how we got 18. So we need
the 300 is it standard?
So when you go to the market, there are different size capacity of PV modules. Now we have some of them that are even 600 watts. So if you're buying a 600 watts PV module, you only need about 9 of them instead of buying 18. If you're buying 300 watts PV module, you buy 18. If you're buying 450 watts PV module, you also divide it and you see the number of PV panel that you need to buy. So there are different capacities of PV modules in the market. So depending on the one that you want to use, there is about 200, there is 250 watt PV module, there is 300 watt PV module, there is 350 watt PV module, there is 400 watt PV module, there is 450 watts PV module. So depending on the one you see or you want to use for your installation.
Right. So in a nutshell, if we got the actual PV,
excuse me, sir.
If we
just hold on for him to finish, please.
So in a nutshell, if we got actual PV size of 5,440 watts, so the person that gave 18 means that is going to use the 300 model, isn't it?
Yes, correct.
So which means that it's not like being static. So the person that used 600 or 350 can get a different values, right?
Correct.
Right. Okay.
All right. Thank you. Okay, go on, please.
Okay, my own question is, this performance ratio of 75%, is it applicable to every type of PV module, or it can be lower than that in some PVs?
It can be lower than that in some PVs.
So what is the standard that we know that we can just assume to take for the performance ratio?
So I will advise that you use about 75 or 70%. It can be lower, it can be higher. But now this is more like is an assumption. You can only know your actual performance ratio when you have finished your installation. It is only when you have finished your installation. So how do we get performance ratio? In our last class, I explained how you get your performance ratio. So your performance ratio is after you've done your installation, maybe after 1 year or after 1 month, you now check the output from your PV panel. If you're expecting your PV panel to produce 5,000 watt hour, okay? If you're expecting your PV panel to produce 5,000 watt hour in 1 month, then after that 1 month, but what you actually see that your PV produced was 3,000 watt hour. In actual production, is 3,000 watt hour. So you divide that 5,000 watt hour, you divide 3,000 watt hour by 5,000. Let me just run that calculation. 3,000 divided by 5,000. So you find out that for that very installation, your performance ratio is 60%.
Please, I want to ask, is it also right to think that performance ratio drops with the age of the PV panel?
Correct.
Okay, so which means, of course, a new PV panel will have a higher performance ratio than the one that has been in operation for perhaps 10 years, 5 years, and maybe even 20 years. So
correct.
as the PV panel ages, the performance ratio drops.
Yes, correct. So some people will tell you, if you look at the technical details of PV model, sorry, there is a graph that they usually show you about degradation. So PV models degrade over the years. So some will tell you that the PV model have a lifetime of 25. It does not mean that after 25 years that the PV models will stop producing. No, it will continue to produce, only that their performance ratio at that point would have reduced to maybe about 20 or 30%, right? So that's what it means. It doesn't mean that they will stop producing after 20 years or 25 years, but over the years, the performance of those PV models degrade. And PV manufacturers will give you a graph of how that degradation happens. After 5 years, this is the amount of degradation that is going to happen on this PV model. So those are the things you also look out for in the technical data sheet of your PV models. So can we try out this exercise 3? So the question is, calculate the actual PV size if the required energy is 10.2 kilowatt hour and the peak sun hour is 5, performance ratio is 75. What is the actual PV size that is required?
It will just be half the numbers now. It's 10.2 is less. Given that the energy required here is 10.2 and the same PSH, the same PR, so it will just be half the number, which is 9 PV modules of 300 watts anyway.
So what we are looking at the wattage of the PV module. What is, do your calculation and tell us what the wattage of the PV module would be. Accordingly, I don't know how you got 846. Okay, so I'm seeing answers coming in. Now this question is asking us for the wattage, not in terms of the number of PV. Of course, you need to know the number, the capacity of your PV before you can begin to divide. Okay, so we're having 2,720 watts, and that's correct. If you're having something different or you're not sure of how we arrive at this calculation, please ask questions so we can clarify. It's a very simple calculation. Just follow this process that we have here, but instead of using 20,400, use 10,200 watt hour, right? The peak sun hour is the same as 5. I think we use 5, and then the performance ratio is 75, which is the same here too. Now there's a trick here. Now let me ask. Remember that the total battery capacity that we need is 20,400 watts hour, or 20.4 kilowatt hour, right? But that does not mean that on daily basis, the battery is going to deliver 20,400 watt hour. You can only take half of this capacity. So if you can only take half of this capacity, do you really need to install a PV module that can charge the 100% capacity of the battery? Since after the first charge, after the first initial charge, you only need to charge that battery to 50%, not 100%. I don't know if the logic is clear or what I'm trying to act is clear.
Yes, I was coming to that question actually. And in addition to that, I also want to ask, given that this capacity we are talking about is a 3 days, 3 days capacity from our initial sizing is a 3 days capacity. And then the peak sun hour that we're talking about is a daily peak sun hour. So why do we have to generate all this when we know that tomorrow again we are going to have 5 hours, next tomorrow we are going to have 5 hours? Is there anything that can guide us in doing a more economical design, so since we know that we will continue to get these sums, on daily basis?
I'm sorry, Abdullahi. I'm sorry, my network was kind of disrupted. Can you repeat your question, please?
Okay, I said, yeah, you just talked about the fact that our batteries were 50% depth of discharge. So we actually don't need to generate this whole energy, I mean, to feed our battery, given that we'll only be charging 50% of the battery. Okay.
All right.
And then I said, but even in addition to this, when we decided this 20,400 watt hour, it was for 3 days with 2 additional autonomous days, right?
That's correct.
And then the peak sun hour of 5 hours is a daily peak sun hour.
Correct.
So if the panels will be up there and continue to work, right? Is there any way, because I really don't need, I mean, 5 hours to charge all my batteries to use it for 3 days. This sun will continue to come out every day, more light. So is there any way that we can do some analysis to say, okay, I don't actually need this number of panels, since tomorrow I'm going to have another 5 hours, next tomorrow I'm going to have another 5 hours? Just to put some economics into your design.
Yeah. I love the fact that you're asking this question, because this is where so that's why it's really, solar systems are really called in designs, right? So you cannot, what works for Mr. A might not necessarily work for Mr. B.
Yeah.
Region, okay. So this is where the economics has to come to play, right?
Yeah.
But for me, I really want us to understand the technologies.
Okay, that's fine. Yeah.
You cannot listen to your clients, and then depending on the budget and the capacity of your client, you cannot begin to play around. Okay.
After all, no two engineers will give the same design. With experience, you give a better design. Different load factor, different diversity factor, different stuff. I mean, over time with experience. Okay, that's
correct.
Fine.
So you can even explain this to your clients, and then for them to understand. Okay, we can actually play around this economically, right?
Yeah, at least I can give different options of designs. Yeah.
Correct.
Okay, thank you.
Yeah. I hope everybody understands what Engineer Abdullahi, I want to believe, is saying here. Because it's very, very important. This is not just a straight bullet. It is, the solar PV designs are specific to your client's need and budget. So what you give to Mr. A might not necessarily be the same thing you're going to give to Mr. B. You can, play around the economics based on the budget and the technology that you want to use. So I want to believe that that works for everyone. So let's move ahead. Is the charge controller. So we are going to size the charge controller. Now, let me also make a remark here that there are some hybrid inverters, inbuilt charge controllers. In fact, if you hear that an inverter is a hybrid inverter, it has a charge controller. That's what that simply means. You need to know the capacity of the charge controller and be sure that the solar panel that you're loading to that inverter is not oversizing. I mean, it's not higher than the capacity of the charge controller. Of course, they will state it. For hybrid inverters, it will be stated the amount of solar panel you can load to that charge. It's important to look at the technical details of your inverter and equipment before you go into your connections. It's very, very important. Otherwise, you may end up endangering the whole installation or having an installation that might not deliver. So it's important to look at all of those technical details. We are going to talk about them. So if it's not clear to you, don't worry, we're going to talk about it. So using the sample load details in the data from the same client that we have been calculating for, of course, we have a battery of 20,400 watt hour. We have a battery voltage of 12 volts and solar PV array of 5,440 watts. So these are all what we have established already from our calculation. So now we want to size the charge controller that will be able to charge this battery. The battery is 12 volts, and then the battery capacity is 20,400 watt hour, and the solar panel is 4,440 watts. So required solar charge controller is equal to solar PV size, which is 5,440 watts, divided by the battery voltage, which is 12 volts. Okay. So if we do that, remember that 5,440 watts, this watt is the same as voltage times current. If you open this wattage, it's voltage times current. So you're dividing by voltage. So if you cancel this voltage current, so charge controllers are rated in amperage, which is the unit of current. Okay, so if you do this division, you will have 53 amps, assuming other losses are neglected. Okay, now when you charge a battery and discharge a battery, there are losses, but so this is the amount of charge controller that you need. So when you go out in the market, charge controllers are rated in amps. And why do we need charge control to your batteries? Okay, you don't want your battery to charge at different voltages. Okay, so what charge controller do is that the voltage and current that is coming, the charge controller helps to regulate the voltage. So if your battery requires 12 volts, the charge controller makes sure that the current that is going into that battery is at 12 volts. If there are excess voltage, so the charge controller tries to convert it to current, and it keeps charging your battery at 12 volts constant, at a constant voltage of 12. If your battery is 24 volts, your charge controller convert excess voltage to current. So that's what your charge controller do. So for this very we are done with the 5 parameters that we need to calculate. We need to calculate the load, we need to calculate the battery capacity, we need to calculate the array, we need to calculate the inverter, and we need to calculate the charge controller. So we have done. This is a charge controller of 453 amps. You may not see this kind of charge controller in the market. So what that means is that you need to buy multiple.
Engineer Chima, please, I just want a small clarification quickly.
Okay, please.
Yeah, you said if there is excess voltage, right?
Yes.
That the panels are supplying, the charge controller will convert it to current, right?
Yes.
And okay, will that now cause the batteries to charge faster than they would have charged? Or I mean, what's the advantage of having excess current?
Yes. So when the current is higher, it means that the batteries will charge faster. Sorry, to charge faster.
Okay.
Yes.
Okay. Just want at least to ask this so that everybody will be on the same page on why excess current has advantage.
Yes. So it to charge the battery faster. So that is it. So when you go out in the market, you might not see a charge controller that rating. You might find 60 amps, 100 amps, in fact, mostly 60 and 100 amps, or as the case, multiple charge controller. But let me say this, and this is why in most cases 12 volt system, you have 24 volt system. Please calculate what the charge controller will be. If you have a 2, do the calculation, please, and let's have the answer.
I can't hear you again. No.
I'm waiting for you to respond. I asked a question and I said, we are working with a 12 volt system because that's the battery we have. Our battery is 12 volts. But imagine that you have a 12 volts, you have a 24 volt system or battery system, right? What is the amp charge controller? How many amp charge controller would you need?
226.66.
Sorry, what? Say that again.
226.66.
Correct. So if you increase the voltage of your system, now let me also make this clear. Is your system voltage. system volt. So if you have 12-volt battery that are connected in series to give you 24, what that simply means that your system is 24 volts, not 12 volts. So you need to put that here, which is 24 volts. So if you increase the voltage of your system, you reduce the capacity of your charge controller. That's what it means. And we know that charge controller costs money. It doesn't come cheap. So if you want to reduce the cost of charge, reduce your charge controller. So that's what I stated here. Note that increasing the battery voltage will reduce the capacity of your charge controller required to charge the batteries. So that is just what I wanted to highlight here.
Hello, sir.
Okay.
Please, based on this thing that you said, so is it possible for us, is it only 12 and 24 that we can make our battery to be? Is it possible for us to collect 3 numbers of 12 volts in series also?
It is
just to reduce our charge controller.
But 36 is rare. 36 is rare. You can have 36. There is 48. The most common are 12, 24, 48. You can also have 36, 3 in series, but it is rare. You have to look at, you know, your system, right? To be able
so we
to.
can do 4 in series.
Yes. You can do 4 in series and have 48. Yes.
So that will reduce the charge controller.
Definitely.
Hello, sir.
Hello.
Yes, sir. Increasing the voltage capacity,
your network is breaking. Your network is breaking. Please repeat yourself, please.
What I'm saying is, you said that, like, if we increase the battery capacity, maybe from 24 volts.
Goodness, is it just me? Can anyone hear him clearly? Because I can't hear him clearly.
We cannot hear him.
The static is too much. The static in his voice is too much.
Yes. Please, Isaac, can you type your question? Is it possible for you to type your question? And I'll just keep an eye on the chat.
Good morning, Mr. Chima. I think what he was trying to talk about, you talked about increasing the voltage of your system, but yes, it has to do with, as you increase the voltage of your system, there's the attendant issue about the number of batteries you are going to also introduce into your system. Because when you talk about a 48-volt system, you're talking about using 4-number 12-volt system, and that increases the cost. So when you want to do the economics of it, is it best to increase the voltage of your system in order to reduce your charge controller, or to find a balance to make sure that your charge controller is still within range in terms of prices?
Thank you very much. Thank you very much for that question. So it has to now do with the capacity of the system you're designing. If you're designing it, if you introduce 4 batteries, it will increase your cost, which means it's a smaller system that you're actually designing. So you can reduce for a lower voltage of 24, right? But if your system is big, I mean, for me, about 48 or 24. So I mean, like you say, you have to look for the balance, look for a way to balance, your design. I don't know if that's.
I think in addition to the question that is trying to ask, because I understand the question. So economically, if you want to strike a balance, is it to increase the number of batteries that will incidentally reduce the the charge controller? In terms of pricing, which one is more economic than which one?
Yeah, I understand the question too, but I think this is left to the designer. We do both alternative designs and check the cost in the market. If you check the cost, you'll see. Because I don't know, unless Engineer Chima knows how much the charge controllers, different ratings cost as compared to how much the batteries cost. But you have to do the both designs and see what works better economically.
Yes, in addition to what Engineer Abdullahi have said, now if you look at the number of battery that is required in your system, and for example, you already established that you need 8 numbers of battery for your system. So in this case, you can say, okay, since I need 8 number of battery, let me work with 48 volts, so I can have 4 in series, and then the 2 in parallel, and you still have your charge controller can be reduced. But if you look at the number of battery, first of all, you need to look at the system. For me, I mean, that's the first point of call before you can now see how you can be able to now walk back to the charge controller and the voltage of your system. Okay, you need, and the number of batteries is about 4. You can decide to go with 24-volt system. So you have 2 of those batteries in series, and then 2 in parallel, and then you still have your system design working effective. You know, it's more of a design thinking or a design thing here, where you need to find a way to balance, you know, between charge controller and the voltage of your system.
Chima, can I ask a question, please, quickly?
My hands are up.
Okay. Oh, before then, Raymond, please go on.
Okay. What are the variables in this equation? Do we want to get the controller smaller? Is it always advantageous? What are the advantages? If we bring the controller small and increase the voltage in the battery voltages can also lead to high costs. Somebody has said so, but the last person that commented said there will be a mixed connection, some in parallel, some in series. Do we know the dangers associated with mixed connections, whether they can lead to surges? Is there no empirical way of establishing that when you raise the voltage, you have decreased the controller size? Is there no relationship in those issues so that we can know how to alter the variables? Which variables especially? Because it appears we have left out current.
Can I come in here, please?
Okay, yes.
Oh, okay. I think the most important variable here you should consider is the cost, you know, because whether you want to do parallel connection in the charge controllers in order to have higher current rating capacity, that's reducing the charge controller selection you do, or you want to put the batteries in parallel in order to also increase the current, or in series to increase voltage, those connections don't have any implication. It depends on what you want. The cost is the most important variable. Okay, I'll give you an example. Like this question we just solved now, we saw that the charge controller required would be 453 amps charge controller. But 453 amps, I tell you, is a very large current, very, very large. In fact, that's why you will hardly find charge controllers at this rating unless you want to use the industrial charge controllers. Most of the, charge controllers you find, like Engineer Chima said, will be 60 amps, 80 amps. So in this case, you will have no choice than to reduce the current rating so that you can have multiple charge controllers connected. And then, like I said, you do different designs, alternative designs. Take the cost and see which one gives you a better cost. So whether you are doing parallel or series connection, as far as I'm concerned, as an electrical engineer, I don't think there is so much, any implication to that. It just depends on what you want to achieve at the end. And what you want to achieve is largely driven by the cost. As an engineer, you have to be guided by cost. Economics of your design is very, very important. So that is what drives it ultimately.
Thank you very much.
I've heard the explanations, but I also think that the functional state of the equipments we choose will depend on the load or the current or the voltage we apply to them. it is also important to take care of that safety aspect.
Yes, you're very, very much correct. Those equipment, that's why I talked about looking at the technical design of those equipment. These days, we have high voltage inverters. In fact, it's common in the market. You have an inverter where, yeah. So there are different technologies in inverter. I don't want to go into that. We are now beginning to see transformer-less inverters, right? Before we used to have transformer-based inverters. So I don't want to go into those technologies of different inverters and their design technologies and what have you. But for a manufacturer to have, done the design and then, tells you that this is the voltage range to which the equipment can work, you have to stick to that voltage range. So if you have gone to the market and procure a high voltage inverter, you need to connect your panels in series to get that voltage that you need to input into that inverter. Whether it is safe or not, I am not a safety certifying agent to say, okay, it is safe or not. But one thing again, I also want to talk about here, since you're talking about variables, is also on the sizing of your cable. So it also has impact on the sizing of your cable, right?
Correct.
Yeah. So the higher the current, the thicker the cable, and the more expensive the cable.
Exactly.
So in fact, that is why you have to try to bring down the current.
Exactly.
Okay.
Because if you apply these higher quantities to a weaker or lower rated cable, they could peel off and ignite fire. So when you said you are not after what happens, safety is one of the conditions for a good design.
As a designer, you need to. That's why I quickly talked about the cable, the cable sizing, right?
Good.
Cognizance of the cable sizing. You cannot have a higher current, and you now use a smaller cable. You're creating danger, right? So all of this has to come into the balance.
Do we have? Excuse me. Do we have a chart from which we can choose? So if you have so quantity, this is the matching controller, etc. Do you understand what I mean?
No, not clear, please. Can you explain further?
There are charts you can look onto if you have, say, 400 amps.
Okay.
You can go to cable ratings and see which cable can handle it.
Okay, yeah, I will come in here, please. I'm an electrical engineer and I've done electrical services design. So there is actually a chart. Even if you want to use Nocaco, for example, Nocaco cable will give you their chart. They will tell you this size of cable, 25 mm square, will take maximum this rating. So there is a chart from electrical background, point of view. So, I understand these things because I'm an electrical engineer and I have done, services design. So if you have a current of that magnitude, depending on the cable, that you are using, all the manufacturers have their charts, and that will guide you to the cable size you are going to choose.
Yes.
Okay.
That's the point I want you to stress. Yeah, stress this.
Oh yeah, there is.
Thank you.
So thank you very much.
Chima, please, a quick one. Somebody just asked here the implication of overcharging your batteries. Please shed some light on that, because if you continue to charge the battery, it gets to a point that the battery will be 100% charged. What happens? Does the system have some kind of intelligence to know that the battery is fully charged and it should stop charging? Or what is the implication of continuously charging the battery? Please shed light on this.
So of course, if continuously charging the battery could put the battery in danger. In fact, it could damage the battery, and that's the reason why we have even charge controllers. I will have battery management systems to actually monitor charging voltage that is considered to have the battery to be fully charged. It cuts off, the supply of current to the battery. Okay, so that's the reason why, in fact, that's one of the functions of charge controller. And of course, you also have a battery management system. So for example, your mobile phones, at the time your mobile phone goes off, that does not mean that the battery has drained completely. But of course, there's a battery management system inside your phone that makes a certain threshold. Okay, so those are the kind of safety measures to protect your battery. But because if these systems are not in place, maybe you don't have a charge controller to monitor the charge of your battery, or you don't have this battery management system that controls the charge and discharge of your battery. It puts your battery at, in fact, your battery can explode, you know, and it can kill the cells, it can damage the cells of the battery and create a whole lot of problems. Okay, so it's not advisable.
All right, thank you.
Okay, so that is about the charge controller.
Sorry, before you go on, would you mind if I ask this question?
Go on, please. Hello, go on. I can't hear you. Are you having difficulty? Okay, so let's just continue. When you get through,
please quickly, a question quickly.
My own question is related to the what terms of the charge controller, the models itself.
Battery management systems. These systems are they? These systems
Ibrahim,
are.
Ibrahim,
Okay.
hold on.
Okay,
Hold on for. Yeah, go on. The fourth speaker, go on, please. We can't hear you again. Okay, Ibrahim, go on with the question.
Please, I just wanted to have clarity. Battery management systems are these functions inbuilt, just like you mentioned, are they inbuilt in charge controllers, or they are separate modules that have to be purchased?
So that's what the charge controllers do. That's what they are designed for, to make sure that your battery won't charge at a constant voltage. If your battery is a 12-volt battery or 24-volt battery, it makes sure it charges at that voltage, and then it also tries to prevent. So they are inbuilt, if that answers your question.
Yes, please. Thank you very much.
Somebody was, I didn't get the name, but he was trying to ask a question. If any of you understand what he was trying to ask, please, you can help so that we can, because sometimes this question also helps interactive. You're asking brilliant and questions that also bring some of the explanation from even some of us who have this field experience. I didn't get the question he comes back. So in this system, this is a
sorry again, my network just went off.
Okay, good to have you back. Go ahead, you're asking a question.
Yeah, the product type. Which one will you, based on their performance ratio? Because some of them have better performance ratio than others. Some wears out in no time than the rest. So which one would you recommend for the batteries, for the models itself, inverter and charge controller? That's what I was trying to ask about.
I would, that's a kind of I would not want to, put any particular products or recommend any particular product. That's beyond the scope of, the training we are trying to deliver. We want to give you the technical details. I mean,
thank you.
And the reason I wouldn't want to recommend a particular product, and if you have a bad experience, it will look like. So please just make your research, and then there are reviews out there in the internet for you to check. That would help.
Very correct.
Okay. So
hello, Jinashima.
Yes, please.
All I could just say is that when we are doing the software application next week, maybe they will have an idea of one of the products they have in the market. But like you said, today Tesla is leading, right? And lithium iron phosphate batteries are the in thing. In fact, the last time we went to Germany for Intersolar, believe me, in a whole conference that have more than 100,000 people, exhibitors, nobody is exhibiting lead acid battery. I'm telling you, it's lithium iron phosphate. That is the in thing. Okay. And so, like you rightly said, it's something you should explore. Our job is to present the technical know-how then somebody's at liberty to explore the market. And I mean, that's just it. Thank you.
Thank you, Engineer Uche. This client, and we have concluded that we did 453 to support 5,440 watt solar PV array to charge 20,400 watt hour battery storage. So that's it for this client. And so let's try this last exercise. Calculate the required charge controller for exercise number 3, assuming 24-volt batteries were used. So now this question is, if you record what we got, the answer we got in the exercise number 3, I think we have 2,720 watts. So calculate the charge controller that we need to support that design. Exercise number 3, we had 2,720 watts. So what is this charge controller that we are going to be needing? Assuming you have a 24-volt system. Do we have answers? 113.33 amps. Correct. So that's correct. It's a simple calculation that needs to be done. Okay, so let's quickly move ahead. I don't know if we're going to finish this. We just have about 20 minutes. Series and parallel configuration of PV arrays. Oftentimes you've heard about series and parallel configuration or connection for both PVs and batteries. So we are just going to brush through them in this module or in this section. So a string of a PV module. Now, when n could be anything, it could be 3, it could be 4, it could be 6. When n number of PV modules are connected in series, the entire string connected modules is known as PV module string. I think we've talked about connection of PVs, PV string. We have certain number of modules connected in series. Then we call them string, PV string. So the modules are connected in series to increase the voltage in the system. So whenever you connect modules in series, you are increasing the voltage. In other way, whenever you connect modules in parallel, you are increasing the current. Let us take note of this. Now, no matter how you choose to connect them, whether in series or in parallel, your total power output remains the same. It doesn't change your total power output. So this is PV connections in series, and this is PV connections in parallel. Your total output, that is maximum power, is 180 watts. And also, when you connect them in parallel, your maximum power is 180 watts. Now, look at how these are connected. This is how you connect PV in series. Okay, I believe you can all see my screen from positive to negative, and then you have a common terminal output from all of them. Okay, and it's now going to your charge controller or your inverter. So in series, your voltage is your voltage of the first one plus voltage of the second module plus voltage of the third module. If you have up to 10 modules connected in series, you keep adding up the voltage, and your voltage of your series voltage is this summation of all the voltages. So in this case, we have only 3 modules, and each module is 12 volts, giving us a total of 36 volts. Okay. And the current remains the same. The current is equal to the current of one of them. So you're only increasing the voltage. The current remains the same. So that is for series connection. Then for parallel connection, you're increasing the current. The voltage remains the same. So this is the current. The current is 5. Now for each of these modules, they have 5 amps current. So the maximum current output from their connections in parallel is 5 amps plus 5 amps plus 5 amps, which is equal to 15 amps. The voltage remains the same. Even if you have 100 of them, the voltage remains the same. Only the current will keep increasing. And the total power output from these 2 connections is the same. This is 12 volts times 15 amps current. That is summation of the 3 modules. Will give you 180 watts. And this is 36 volts times 5 amp current. Will give you 180 volts. So this is how PV are connected in series and parallel. And this also is applicable to battery system. The same way you connect this PV system are the same way batteries are also connected in series and parallel. And the same thing applies if you're increasing the voltage or the current. So this is for battery. Now this is a 12-volt battery. You know, I talked about how you connect two 12-volt battery to get 24 volts. So this is it here. If you have a 12-volt battery and your inverter is 24-volt inverter, you need to connect two batteries in series to get 24. So this is how you connect these two batteries in series to get 24. So these are the terminals you actually take into your inverter, and not one of them, and not from a single terminal. So this is how you connect in series. You could also have series and parallel connection. So you want to increase the number of batteries in your system. Now you connect two in series, you've gotten your 24 volt, but you need more batteries in the system. You have to keep connecting those batteries in parallel so that you don't exceed your 24 volt. And this is how you keep connecting them in parallel to maintain your 24 volts, but your current, the current is increasing. So this is how you do your parallel connection, and this is how you do your series connection. This is how you do your series and parallel connection. So if you're looking for 20, so like I said, it depends on the voltage of your individual battery. So in this case now we have 6 volts, and we still want to have 24 volts battery. 24 volt system. So we have to connect 6 of them. We have to connect 4 of them in series to have 24. And the same thing is applicable here. So this is series connection, whereas this is series and parallel connection. So this is for battery. So this is a nameplate of or technical details of a solar panel. I just took a picture of this so that we can see that all that we've been discussing about, you can also find them when you look at the technical details of your solar panel. We talked about the open circuit current, open circuit voltage, maximum power current, maximum power voltage. All of those details are provided in this panel. And in this panel, we can see that the rated maximum power, that is Pmax, is 320 watts peak. That is the rating of this panel. So this is just to make us understand that this calculations that we are doing, or this technical data that we are discussing about, are actually what we need to do a proper design of a system. So let us look at an example. Now, to understand these steps in a more mathematical way, now the steps you're talking about in terms of your maximum power output from your solar PV system, looking at the ratings, from the solar panel. Let's take an example of a power plant. Now, this power plant is 2 megawatts. This is huge, right? 2 megawatts, in which a large number of PV modules are connected in series. A large number of PV modules are connected in series. Now, we have a 2 megawatt inverter in the system. So 2 megawatt inverter can take input voltage between 6 to 900 volts. 6 to 900 volts. Now, determine the number of modules to be connected in series to obtain a maximum power point voltage of 800 volts. So 800 volts is within 600 and 900. So we want to connect certain number of panels in series. And the question is asking us, how many number of panels do we need to connect in series to get 800 volts that we can feed into this inverter? Now, also determine the power delivered by the PV array. Remember, when you connect certain number of PV modules in series, you have a PV array or PV string. Now, they say you also determine the power delivered by the PV array. Now, the parameters of the single PV module are as follows. Now, this is the parameters. Open circuit voltage of the PV is 35. Voltage at maximum power point is 29. Short circuit current is 7.2. Current at maximum power is 6.4. Now let me ask us, what is the maximum power output from this module? It is not given here, but we can calculate it from here. What is the maximum power output from this module?
That will be the maximum voltage by the maximum current,
which is
the maximum current multiplied by the 29 volt by 6.4 amps will give us the maximum voltage, maximum power.
Okay. So is anybody having challenge with this? How to calculate the, how to calculate the maximum power output from this system? You're calculating the maximum power output voltage by the maximum current output current, and not your open circuit current and open circuit voltage, just so we're clear about that. Okay. So the first calculation in solving this, the first thing we need to do is to determine the maximum output from each of the PV panels. So maximum power of the module is 29. Okay, Lanre, you raised your hand.
Yes, are we assuming that the system is a single phase? I'm just asking.
When you say single, I talked about single and three phase.
Yes.
Okay, so it was not given to us here, but we want to assume that it's a single phase.
Single phase of 2 megawatts? I'm just asking.
So this is, now the purpose of this is for us to understand series and parallel connection and the power output, right? If you're looking at the rationale for 2 megawatts to be a single phase, I mean, that is not the purpose of having this example, right? But of course, for having a 2 megawatt system, we all know that it has to be three phase, right? But it's not, now, let me also state here that when you're having an input into an inverter, it is the output that will not tell if it's a three-phase inverter or single-phase inverter. But in this case, it should be a three-phase inverter. But we are talking about the PV input into this inverter. I don't know if that's clear.
Please come again.
The inverter itself, for inverter to be 2 megawatts, ideally that should tell you that it's a three-phase output inverter.
Yes.
But we are not looking at the output of the inverter. We are looking at the input into the inverter. So the question you're asking is beyond the scope of this example that we are solving.
Okay. If it is for that purpose, no problem. I just want to clarify.
Yes. Yes. So for a 2 megawatt system, the output ultimately, the inverter ultimately has to put, the output has to be three phase. Okay, so let's continue. So like I said, the first thing that needs to be done is to calculate the power output from each of the PV module. And once we do that, we find out that each of the PV module is 185.6 watts. That is the output, maximum power output from the PV module. Now the question is asking us to calculate the number of PV modules that will be connected in series. Now, number of PV modules to be connected in series is equal to the voltage of the maximum voltage, is equal to the maximum voltage of the array. Okay, now we are given that the maximum voltage of the array should be 800 volts, right? Divided by the maximum voltage of the module. Maximum voltage of the module is 29. So once we do that division, 800 divided by 29, we have the number of PV module is 27.58. Of course, we have to increase it to a higher integer, which is 28. So if we increase it to 28, what that does is that it's also going to alter the voltage. Remember we are told that it's 800 volts. If we increase it, so if we multiply this number of panels by the voltage, that is 29, we are going to have 800. But you cannot have a 27.5 number of PV panels. So we have to increase it to a whole number, which is 28. Now, if we increase it to 28, it ultimately also changes the voltage slightly higher than 800, but it's still okay because the inverter can handle up to 900, but it is still okay. So take the higher integer value of 800 modules. Due to the higher integer value of N, the value of the voltage of the array, that's the maximum voltage of the array, and the voltage of the this should be the voltage of the system, will also increase. So now, to be able to calculate how much increase that will happen, That will be the voltage of that's the maximum voltage of the array, is equals to the voltage of the module times N, which is 29 times 28. You have 812. I don't know if this is clear. I mean, the rationale for us to, recalculate the maximum voltage of the array, I don't know if it is clear. Because of this approximation we did here, we need to know how it's going to affect the final voltage input. Our target is 800, but we did a small approximation here. We want to see how it will increase beyond our required voltage. So that's what we just did here, and it's 812, which is not still within the range. Now, the question also asks us to calculate the total power of the PV array. That is the total power that is going to come out from that series connection. Okay, so we have 28 numbers of PV modules, 28 numbers, and each of the PV module is 185.6 watts. So we'll just do a straight multiplication. If we multiply 28 by 185.6, we are going to have 5,196 watts, 0.8 watts. So this is output from that PV array. Now, you can see that this output is not even up to 1 megawatt. So what this means that there has to be another series connection of which you have to now do a kind of you have to parallel, to be able to, get, the kind of output. Maybe if you're looking at 2 megawatt, actually, if you want a 2 megawatt output from that inverter, okay, you need to increase your your PV module. But this is just for an example. So thus we need 28 PV modules of 185.6 watts to be connected in series, having a total power of 5,196.8 watts to obtain a desired maximum voltage, maximum PV array voltage of 800, even though we overshot this 800 by 12. So we had 812. So this is just another example. Calculate the number of modules required in parallel to obtain a maximum power current of 40 amps. Now the system voltage is 14 volts. The parameter of a single PV module is as follows. Now this is the parameter of a single PV module. Okay, so first of all, let us try to understand what this question is asking us. The number of PV modules that you require to connect in parallel, not series. So that you can, remember when we are connected in parallel, we are trying to increase the current, not the voltage. If we connect in series, we are trying to increase the voltage. So in this case, what is the number of PV modules that we can connect in parallel to get 40 amps current? That's what the question is asking us. And this is the detail of the PV module. Okay, so to get the number of the PV module that we need to connect in parallel, we need to divide the total array current, which is 40, by the module current. Okay, so the module current in this case is the maximum output of the module, maximum power point current, which is 6 amps. So if we divide 40 amps by 6, we are going to have 6.6. So this is the number of PV modules that you need to connect in parallel. Okay, but you cannot have 6.6 number of PV
Mr.
modules.
Chima, sorry, please, can I interrupt you for a second?
Okay, please, go on.
The first example, we did not, the maximum power is not up to 2 megawatts. That means the design is not sufficient, right?
Yes.
Okay, fine, all right, okay.
Okay, so let's proceed. So in this case, you need about 7 number of panels to be connected in parallel for you to actually have this 40 amps current that you need to feed into the system. So this is an assignment, more like exercise that we can do. We can try our hands on. This is similar to what we have done, the calculations we have done here. So calculate the size of a PV panel, inverter size, battery bank, and charge controller. Okay, this is more like trying to try your knowledge on design. So we want you to design a system. Tell us the size of the PV module, tell us the size of the inverter, tell us the size of the battery bank and charge controller required for the following clients. Now the client load is 137.55 kilowatts. That is the load. Now the energy required, the energy storage that is required for 1 day is 1,000 1,032.625 kilowatt hour per day. This is large. This looks like a factory. So it's also telling us to consider 1 day of autonomy for battery storage. Okay, so we just want you to, on your own, just try out, just to test the level of your understanding of the design process that we've talked about in today's training. If you have difficulties, you can reach us, through the WhatsApp. You can make a call at a convenient time. But in all, when you finish solving, you can as well post your answer on the WhatsApp group. We have a WhatsApp group, and I want to believe that every one of us is in that WhatsApp group. So once you're done, post your answer. If you need clarification, please speak up in the WhatsApp group, or you can even reach out to Engineer Uche or myself. At a convenient time, we can, throw more light and further explanation to this. So it is 12 o'clock on the dot, and I think we managed our time very well, and we've come to the end of today's class, today's training. Thank you very much. I'm Engineer Chima, as I have introduced earlier, and I want to really appreciate you for your contributions and active interactions. I really enjoyed today's class. I learned from you. For every one of you who has contributed, I'm really grateful. And okay, Raymond, you have your hand raised.
Engineer Raymond.
Okay, go on, please, Engineer Raymond.
Yes, Ogara.
Oh, thank you.
Yeah, I missed part of the lecture, but I've seen the previous lecture sent in a package. How soon are we expecting this one so that we can make the connections necessary?
I lost the later part of your question. You say you missed some part of the lecture.
Yeah, I missed the opening parts.
Okay.
But I'm saying that the previous lecture, the last week's one,
okay,
you send the entire lecture.
Yes.
Together and promptly. Can we have benefits for this particular lecture today so that we can make the necessary connections between the lecture?
Yes, sure. The video will be shared with you as soon as it becomes available, and the material will also be shared with you.
Thank you.
I want to ask this question. Please. The question you said we should answer, is it in the material sent this morning?
Yes.
Okay.
It is.
Engineer Chairman.
Okay, Adolphus, go on.
Yes, please. A couple of things. One is, how do I get into the WhatsApp group? I'm not in that WhatsApp group. I can't find your link. And secondly, where do you send the material? Is it only the ones I saw?
My number is displayed on the screen, and I'm sure you may also have Engineer Uche's number. Try and reach Engineer Uche. If you can't reach him, then my number is on the screen. I will make sure that you're being added to the WhatsApp group. Okay. And on that WhatsApp group, a lot of resources and information are shared on that WhatsApp group. Okay. And that's where most of the materials are dropped.
Okay.
Yeah. So that is it. Any other question?
Yes. Can I? Yeah. Two things. So for those that will be added now, is it possible for you to reshare some of those materials? Because if you add some new patients now, you will discover that all the information you've added before is not going to be seen. It's an appeal anyway. Then number two, based on this design of this PV panel, is there any software we're going to use in this training, please?
Okay, so for the benefit of those who are going to be added to the group, I will appeal to Engineer Uche to please send the previous videos and materials so that everyone can have access to them. So that will be considered. And the second question about software, yes. If not, I think by next Saturday, we're going to be talking about software that you can use for designs But again, software is garbage in, garbage out. You need to understand the fundamentals, which is what we have done between last week and today. Okay, if you don't understand what we have done between last week and today, you may not be able to use those software, because when you get to those software, you still see you still meet performance ratio, you will still meet peaks on hours, you still meet all of this detail that we are talking about. You are still going to meet them in the software. So you need to understand what we've talked about between last week and today to be able to even use those softwares. And for me, I'm not a very big fan of softwares. I can, do some of this calculation on Excel because I understand, the arithmetic behind the softwares. I can do them, but again, it doesn't make nonsense of the software. The softwares are very, very helpful, right? They're very, very good and helpful. So we're going to be talking about softwares next week.
All right, thank you very much. But just to add to what you've said, for those that might maybe travel, maybe leave our dear country, maybe to a place like UK and maybe Western countries, I tell you the truth. Even if you know all of these theoretically and you can use Excel, do everything mathematically, and you want to work in a company, they will tell you, do you know this very software? And incidentally, it's going to be the software you're going to talk about. So I totally agree with you that the fundamentals, you must on the theoretical framework and the fundamentals of what we need to do with the software. But software becomes very, very important because today's world, they believed that what software have done, take for example, if you want to publish an articles or materials on some of these things, and you said, from my theoretical, I use pen to calculate this and all of that, sometimes the reviewers, they're not going to accept it. But if you mention a particular software you've used, and then in the end, you just put it clear that based on the software, maybe you use some variables and alternate it and get the graph out. It will be very, very helpful. That's why I mentioned that. But I totally agree with you anyway. Thank you.
Absolutely. The softwares are really important for the fact that sometimes when you run some simulations on this software, because there's a lot of data that the softwares can access, so they can also help you to optimize your design. So that's not to say this, like I said, the softwares are very, very important. But on the basics level, you just have to do some of this calculation. Maybe you want to calculate your energy yield, and assuming you know some of the climatic weather condition, because this is where the software also becomes handy. They can once you locate your project, the project location, they already have a database of some of the climatic weather condition of the region, and they can also use it to simulate your energy yield and then be able to give you a more precise output. So it's really important, and that's why we're also going to talk about them in the coming week. So thank you very much.
Sorry, Mr. Engineer, these videos that you are recording, can you compress them in some video applications that we can have in our system? Because anytime I have to go to YouTube to watch the video again, I mean, why does it have to be on YouTube always? Can't you just compress the video and give it to us so we can watch over and over again?
Let me come in here. There is a way you can also save video from YouTube. Once you are there, you can just click save from the net. It will go to another